This video focuses on finding the absolute extrema of a function of two variables on a restricted domain. In order to do that, we need the extreme value theorem, which states a continuous function f of xy on a closed and bounded set R in the plane attains both an absolute maximum and an absolute minimum value. So if we have a function of two variables on a restricted domain, there will be at least one point that gives us an absolute maximum output of the function, and then at least one point that gives us the absolute minimum output of the function. It's important that restricted domain is closed and bounded. Closed means that it contains the boundary points. So if it did not, that would be considered open. And that the set is bounded, which means that it is finite. Okay, so for this to work, the restricted domain, the region that we are working over, has to be closed, including the boundary points, and bounded, finite. If those two things are true, then we will have an absolute maximum and an absolute minimum of the function. In order to find the points, we're going to let z equal f of xy be a continuous function of two variables defined on a closed bounded set R, and assume the function is differentiable on that region. To find the absolute maximum and minimum values of the function on R, we're first going to determine the critical points of the function in R and calculate the function value at each of these critical points. So the critical points have to be in the region. If the critical points are outside the region, we're not going to include them in our computation. If the critical points are on the boundary of the region, we're not going to include them in our computation. Right? And that's a matter of definition. So the critical points have to be on the interior of the region. Notice we are not running the second derivative test here. We are simply finding our critical points and plugging them into the function to see what their output is. Right? So we skip over the second derivative test when we're finding absolute extrema. And the critical points, as a reminder, they are found by saying that either the partial of x equals 0 and partial of y equals 0, or these could be undefined. Right? Those are the two ways that we have critical points of a function of two variables. And then step 2, find all extrema of the function on the boundary of R. So our restricted domain is going to have a boundary. Most of the restricted domains you're going to see are going to be triangles, squares, rectangles, circles. Could be a more complex shape, but typically it falls into that category. So we have boundary curves around each of those restricted domains. And our goal is to find the extrema on the boundary of the region. That really equates to running single variable extreme value theorems along each edge of the region. Okay, so find all extrema. This is really just going to be Calc 1 extreme value theorem, which is saying single variable extreme value theorem. And we want to put a reminder to ourselves, don't forget endpoints. Right? The endpoints of each boundary curve of the region need to be included, the same way that the endpoints were included when you were doing single variable extreme value theorem. And then, as our conclusion, the largest value that we get as an output is the absolute maximum, and the smallest value is the absolute minimum. Okay, so now that we have a plan, we have to put it into action. And the one thing I'll say before we even look at our first example is the difficulty in these problems comes from the length and the amount of details, not really from the computation, or most of the time, not from the computation. So find the absolute extrema of the function x squared plus 3y minus 3xy on the triangular region R defined by 0, 0, 2, 0, and 2, 2. First thing I prefer to do is draw out the region, just so I can visually see where the critical points should be. So 0, 0, 2, 0, 2, 2. So 0, 0, 2, 0, 2, 2. Connect our points. So there is our triangular region. So first thing, let's find the critical points of this function and see if they fall inside of that region. So partial with respect to x is 2x minus 3y, that equals 0. Partial with respect to y is 3 minus 3x equals 0. So we can solve the partial with respect to y and get x equals 1. And if we plug in 1, we get 2 minus 3y equals 0. So y equals 2/3. So 1 2/3 would be like there. So that is inside of the region. We're going to put that in our list of potential points for the absolute maximum or minimum of this function. Right? So we'll make the list on the right side of the page. So now that we found the critical points, now step 2 is to find any extrema along the boundary curves. So in this case, for the triangle, there are 3 boundaries that we have to work along. The first one is y equals 0. Then we have x equals 2. And we have y equals x. Sometimes you'll also see them include restrictions here, whether it be domain or range restrictions. I think we can just use our picture to determine if the critical points are in the region. But it is more mathematically defined if we would say y equals 0, x goes from -2 to 2, right? That's what it would look like. But let's just keep it simple. This reminds me of the path approach for limits, because we're going to say we're going to go along y equals 0 to find any extrema. So we're going to reduce the function to a function in terms of only x. So if y is 0, the function is x squared. So f prime of x equals 2x. We set that equal to 0, x equals 0. So 0, 0 would be a potential point of absolute max or absolute min. Now, technically, we shouldn't count this as an extrema point because it is the endpoint of that boundary curve, but we're going to include it anyway because it's an endpoint. So regardless of how we think about it, 0, 0 needs to be added to our list. But at the same time, so 0, 0, the other endpoint of that boundary curve is 2, 0. So 2, 0 gets added to our list. Okay, so we found or tried to find any extrema along y equals 0. We found one, but it happened to be the endpoint. So really, we're not including it because of our work. We're including it because it's an endpoint. And then we also include the other endpoint, which is 2, 0. Now we'll go, I'll use a different color. So now we'll go along x equals 2. So that reduces our function to a function of y. So that's going to be 4 plus 3y minus 6y. So f of y is 4 minus 3y. Take the derivative, -3. That does not equal 0. So there are no points that we have to consider along x equals 2 other than the endpoints. So one of those endpoints was already put on our list at 2, 0. The other endpoint is at 2, 2. So we add that to our list. So 2, 2. We're building our list of potential points where the absolute max or absolute min is going to occur. One last curve. We're going to go along y equals x. So I'm going to reduce it to a function in terms of x. So that means we have x squared plus 3x minus 3x squared. So f of x equals 3x minus 2x squared. Take the derivative. 3 minus 4x equals 0. So x equals 3 over 4. That is going to be on the line, right? 3 over 4. So that's like the point right there because y equals x. So we add that to our list. So 3 over 4, 3 over 4. Now that we have our list of potential critical points, now we have to evaluate the function at each of these points. So evaluate the function at these 5 points. So right now I'm just filling in notation. So f of 1 comma 2/3. So we go up to our function up there. So we'd have 1 plus 2, which is 3, minus 2, which is 1. And feel free to write it out. I'm just trying to save a little bit of space here. 0, 0, that's going to be 0. F of 2, 0 is going to be 4. F of 2, 2, back up to the function, so we'd have 4 plus 6, so that's 10. And then minus 12 is negative 2. And then f of 3/4, 3/4, this one I will write out just so I don't make a mistake. So we'd have 9 over 16 plus 9 over 4 minus 3 times 3 times 3, so 27 over 16. So this is really 36 over 16, 9, 18 over 16, 9 over 8. So you see a lot of the work here is just plugging in the points that we found with calculus. Now once we've done that, now we have to come to our conclusion. Which of these values is the absolute maximum and which is the absolute minimum? So here, 4 is the absolute maximum of the function on this restricted domain, and negative 2 is the absolute minimum. And 4 occurs at the critical point 2, 0, which was one of the endpoints of the boundary curve. And then the absolute minimum was at 2, 2, which is also another endpoint. So see, if we did not include these in our list, we would have missed the points that should have been the absolute maximum and absolute minimum outputs of the function. Okay, next up. Find the absolute extrema of the function x squared plus y squared plus xy squared on the given region defined by negative 1 is less than or equal to x less than or equal to 1, and the same for y. So our region, draw it out in the xy plane. So negative 1 to 1, negative 1 to 1. So we have a square region, 1, negative 1, negative 1, 1. So we have a square region that we are looking at. First thing, let's find our partial derivatives and see if there are any critical points inside of the region. So partial with respect to x is 2x plus y squared. We're going to set that equal to 0. Partial with respect to y is 2y plus 2xy equaling to 0. We can use the partial with respect to y, factor out 2y, 1 plus x equals 0. So either y equals 0 or x equals negative 1. So if y equals 0, then that means we'd have 2x equals 0, x equals 0. 0, 0 is right in the middle of our region. So we put that on our list, 0, 0. And then we have to check if x equals negative 1, what happens? So we'd have negative 2 plus y squared equals 0. So that means y equals plus or minus the square root of 2. Now the points negative 1 square root of 2 and negative 1 negative square root of 2 are going to be outside of this region. Since square root of 2 is about 1.4, that's going to be 1 point would be above, up here, too high, and 1 point would be down here below the region. So we're not going to include those 2 points, right? So this is what we were speaking about earlier, where the critical points have to be inside the region. These 2 critical points not going to be added to our list. Now we have 4 boundary curves. So we have x equals 1, x equals negative 1, y equals 1, y equals negative 1. We have to go along all 4 of those boundary curves. Okay, so let's start with x equals negative 1, just because it's going to give us something unique, and we'll start our conversation there. So if if x equals negative 1 rather, the function's going to be in terms of y, and if x is negative 1, we'd have 1 plus y squared minus y squared, which is just 1. Which means that f prime of y equals 0, which always is equal to 0. So this is a constant curve, right? So this is a constant, which means all the points along that boundary are going to have the same output. Now, what that means for us is if one of those points gives us an output that's an absolute minimum or absolute maximum of the function, that means every point along this boundary curve would do the same. So in our list, we're going to write the critical point as -1 comma a, where a is between -1 and 1. Right? So we're basically generalizing the set of critical points that are along this curve. So I'll take red. So basically every point along this boundary curve, including the endpoints, is a potential point where the function has an absolute max or absolute min. Not the easiest thing to wrap your head around, okay, but that happened because the function was constant along that boundary curve. Now let's go along x equals 1. So then our function in terms of y is going to be 1 plus y squared plus y squared. So that's 2y squared plus 1. Take the derivative with respect to y, we get 4y equal to 0, y equals 0. So 0, 1, or 1, 0 rather, 1, 0 right there, that's a potential critical point. And we also have to include the endpoints of x equals 1. So we're adding 3 more points to our list. So 1, 0, 1, 1, 1, -1. Now we have to go along y equals 1. So our function is going to be in terms of x. So if y equals 1, that means we have x squared plus x plus 1. X squared plus x plus 1. I changed the order of those second and third terms so that we can differentiate more quickly. So 2x plus 1 equals 0. X equals -1/2. So we have -1/2, 1. -1/2, 1. If we go, we've already included the endpoints of that boundary curve, so we don't have any additional points. But -1/2, 1, so right there, that's a potential point. And then one last, we have to go along y equals -1. So along y equals -1, right? So for me, it's really just the pace of these problems. It's very methodical. Boundary curve, find any critical points, endpoints. Go along the next boundary curve. So here at y equals -1, we also have x squared plus x plus 1, since both y terms are squared. So f prime of x is 2x plus 1 equaling 0. So x equals -1/2 again. So now we have, want it to be black, let's stay consistent with our color here, -1/2, -1. So there is our list of critical points. Now, next up, we have to evaluate the function at all of these critical points, but I'm going to copy them and bring them to the next slide, because I want to evaluate them while also looking at the surface. So let's paste them in. Okay. So what you can see here is I've graphed this surface, this function, over the domain that we've been finding our critical points on, so that we can visually see why we have to go along the boundary curves and how this all relates to one another. So first, let's just evaluate the function at each of our critical points, and then we can connect it to the graph on the right-hand side to give us a little bit better understanding of what's exactly going on and why we have to go through all this work. So at 0, 0, we get 0. At negative 1a, we'd get 1 plus a squared minus a squared, so that's just 1. At 1, 0, we get 1. At 1, 1, we get 1 plus 1 plus 1, so that's 3. 1, negative 1, we'd get 1 plus 1 plus 1, so that's also 3. Negative 1/2, 1. So this one I'll write out. So it's going to be 1/4 plus 1 minus a half. So that's going to be 5/4 minus 2/4, so 3/4. And same thing here, because our y terms are squared, so that's not going to change either of those values. Okay, so we have 2 points that give us an absolute maximum of 3. And we have 1 point which gives us an absolute minimum of 0. So if we look at the graph, so the square, the region, so I'll move my picture over. So the region that we're working under, right, so there's our square, okay, from negative 1 to 1. So the 2 absolute maximum points are right there at the endpoints of boundary curves. And we can see that they have the same output, so that's those 2 points there. This constant point, where we had to include all of the points along the boundary, so we can visually see that's back here. All of those points have the same output. So if those points were to be the absolute maximum or the absolute minimum of the function, we'd have to include all of them. Right? And this is a nice way to express all of those points. Okay, call the point negative 1a and give a range for a. The absolute minimum is the critical point we found right there at the, or in the middle of the surface at 0, 0. And then the other points, 1, 0, and then 1, 0, that's here. And then the negative 1/2, so that's back there. So there's a point there, and then covered by the surface. So those are all those critical points that you were finding as we went through the process. So I think it's important for at least one of the examples for us to visualize the surface, because it gives us a better understanding of why we need to go along the boundary curves to find all these critical points, right? And what exactly we're doing when we're finding them, right? So all our critical points, our function values, and that allowed us to classify our absolute max and absolute min. One more example. So find the absolute extrema of the function x squared minus y squared plus 4x on the region R defined by x squared plus y squared less than or equal to 9. So here our region is a circle of radius 3. First thing, let's find our critical points and see if they're inside the region. So negative 2x plus 4 equals 0. And the partial with respect to y is 2y equals 0. So here x would be 2 and y would be 0. So 2, 0 right there. That is inside the region. So that's first point on our list. Next, we have to go along the boundary. And this is where circles can become a little bit more complicated than, say, a triangular region or a square rectangle, because the boundary is just one smooth circle. So we have a few options here. We can choose to solve for the upper semicircle and the lower semicircle. So we could solve for y equals the square root of 9 minus x squared for the upper and the negation of that for the lower, and do those 2 separate paths. That works. We can solve for x and do the right and the left. That would work. And you notice there would be endpoints there. In this case, including a more creative approach that could be helpful and save some time, if we notice in our function there's a y squared term, so instead of separating into the upper and lower, we're just going to solve the boundary curve for y squared, because then we can do a direct substitution. So here we're going to go along y squared equals 9 minus x squared. It doesn't always happen that this technique would work out nicely, but when it does, it saves us having to go over 2 separate paths, like the lower and the upper, or the right and the left. The one thing we do have to be aware of here is if we were to solve this, x is bound from 3 to -3, -3 to 3, the way I wrote it. Okay, so that does mean that -3, 0 and 3, 0 are going to be considered endpoints here. So we can just put those on the list now so we don't forget about them. So -3, 0 and 3, 0 here. And again, just to clarify that, if we were to solve for y equals the square root of 9 minus x squared and the negation of that, -3, 0, 3, 0 would be the endpoints of either the upper or the lower half of the circle. Now, going back to this more creative approach where we're just saying y squared equals 9 minus x squared, that means the function in terms of x is 9 minus x squared minus x squared plus 4x. f of x equals 9 plus 4x minus 2x squared. Take the derivative with respect to x, we get 4 minus 4x equals 0. So x equals 1, which means y squared equals 9 minus 1, y squared equals 8, y equals plus or minus, I will simplify the radical here to 2 square root of 2. It doesn't really make a difference. In certain aspects, leaving it as square root of 8 might actually be easier for evaluating. But we'd have 1, 2 square root of 2, and 1, -2 square root of 2. So there are the 5 potential points where the function's going to have either an absolute maximum or an absolute minimum. Now, off to evaluating. And again, it's just the amount of steps here. I don't think anything individually is really challenging. It's just the fact that there's a lot to do with these extrema problems, the absolute extrema problems. So f of 2, 0, so that's going to be -4 plus 8, so that's 4. And then -3, 0, that's going to be 0 minus 9 minus 12, so -21. And then 3, 0, it's going to be -9, but now plus 12, so that's 3. And then the square root point, so 1, 2 rad 2, so that's 8, minus 1 is 7, and then plus 4 is 11. And it will be the same because we're squaring y, and the negative is not going to change the output. So there are all the outputs of the function. So we have 2 points that give us an absolute max of 11, and 1 point which gives us the absolute minimum of -21. And notice one of those points was an endpoint of a boundary curve. So if we were to leave it off our list, we would have missed the point that really is the absolute minimum value. Okay, so really just a method. Find our critical points, make sure they're inside the region, go along the boundary curve, however many curves make up the boundary, make sure you include your endpoints, and then once you have that list, evaluate the function, and then just look at your outputs. The largest output, if it happens multiple times, there would be multiple absolute maximums, like this case, and then your lowest output is going to be the absolute minimum. So from here, it's just practice, seeing different regions, different functions, but the method doesn't change. So get that practice in, feel comfortable with it. These questions aren't fast. Hey, it's just a matter of paying attention to all those details.